Hello, this is our code review for our Deep Learning for Computer Graphics final project. My name's Eric, and I'm working with...
My name is Jacob Roberge.
And I'm Kasra.
And let's just start from the beginning of our script. So here are all our imports. You see we are using PyTorch, some NumPy, and Gym, which is OpenAI's emulator. So here we use Gym to make the environment for Breakout. We have an RGB output, which is just an RGB screen data. We have a frame skip of 7, so that means for every frame we are actually skipping over 7 frames. Or for every action we are skipping over 7 frames after that. So yeah, here we can see the action space, meaning there are 4 valid actions in Atari Breakout. And you can see this method right here just randomly picks one of those 4 actions. Here are all the action meanings too. This is no action, fire, and then the right and left movement buttons. And then finally down here, we configure our program to use GPU programming when necessary. And now I'll pass it out to Kasra for the convolutional neural network.
All right. Thank you very much, Eric, for carrying the conversation up to here. I'm going to talk about how we are basically getting the state of the system. As you might remember from our presentation, we actually are modeling the game as an MDP. State is one of the necessary parts of the problem. We are giving inputs, images as inputs to our Q-learning agent to extract the relevant features from the images, which would be the position of the ball, position of the bricks that we're trying to destroy, and also the position of the paddle. We are using convolutional neural networks to extract these features. We have experimented with various different architectures, and we have settled on 3 convolutional layers. Where we have kernel size 3 set for all of them, and we have a straight of 1. We are trying to basically downsample our images into a lower dimensional feature space to be able to reduce the number of parameters that we have to train for, which ultimately leads to a faster performance of our algorithm. We experimented with various architectures. We ended up using batch normalization, which gives us 2 things. 1, the problem is going to be more general. 2, our training is going to be way more stable with batch norm. Therefore, we have 3 conv layers followed by batch normalization. And we are using ReLU activation function, followed by, in the last layer, we have a fully connected layer whose output is basically being fed to the RL agent. With that, I'm going to hand it over to Jacob, who is going to talk over the Q-learning algorithm in the code for us.
Sure, thank you. And we can scroll down here. Alrighty, for the hyperparameters. Just talking over quickly, what are the most important hyperparameters? We have a gamma of 98, so that's our discount factor in our Bellman equation. We have an epsilon of 1, which is incorrect. We actually hard-coded the epsilon of 5%. 5% of taking a random action. And then we have a max history length of 10,000, which is any more than that, and that's above 10 gigabytes, which is above the GPU, which is more memory than the GPU that we use to train has. Then we update the stable model every 500 steps. And as you see here, we are using a smooth L1 loss and a atom optimization and a learn rate of that number. Then for Q learning agents, we are first initializing a DQ. A DQ is very nice because you can just give it the max length, and that's going to be our replayed memory. Then we're just initializing update stable counter and the target model. And then for that target model, we are giving it the current cube model's current weights. Then we have a process image function. This just takes the RGB 180 by 140 image, I believe it is, and just cropping the outsides of it, downsampling it, converting it to grayscale, and then we need to turn it into a float 32, and we are then we're dividing by 255, so the values are 0 to 1, which are better when inputting it into a model. Then we have to swap the axes, just makes it, which is required for the PyTorch. Then test model, this is just a quick function, so we could actually see how well it plays. We'll show that later on in action. Then we have two main functions when training. We are first generating the data set. This function generates for a full game of Breakout. And our second function is training. This will be training for X amount of iterations, each iteration training a full batch size. All right, for generate data set, we are first initializing the environment, resetting it. We are initializing a observation memory. It's just a small DQ of size 4. And we have to fill out that DQ, and this will be important for inputting it into the model. And while the game is still running, what we do is we concatenate all of the images in the observation memory into the first dimension. So that means that the image that we're putting into the model is a 4-channel image. Then with a 5% chance, we are taking a random value, or a random action, I mean, or we are taking the action that is the argument max of the model. Then we are taking that new observation, we're appending it to the observational memory, and we are concatenating the next state here. And we were having some issues with the Breakout environment where a lot of the times it would get stuck for an extended period of time. So instead of having the replay memory be polluted by all these frames that are exactly the same, I just continue for any frames that are exactly the same for the next state and the previous state. And then if it's not the same, we will append all the current observations. The current observation, remember, is the concatenated 4-channel observation, and the action for that specific state, the reward, the next observation, which is also a 4-channel concatenated image, and if it's done. Then, if done, we will break out of it, and if the function is getting called for more than one round, then it'll iterate over that round too. Then, for training, we will be taking in X amount of iterations. For each iteration, we will be checking to see if the target model needs to be updated. If not, then passing through that, we will be sampling randomly from the memory for X amount of batch size. Our batch size is 32. For each of the current observations, we are concatenating it to make it a batch size of 32. And the same thing for the next observation. So this means that the mini batch observation and the mini batch next observation has a dimensions of 16 or 32 for 32 batches, and a 4-channel image, and then the dimension or the shape of the images. Then we are taking the Q values from the model and the Q values from the target model. We are enumerating through the mini batch, and then for each of the slices of that mini batch, if done, the active Q is done, and then else we will be taking the max of the stable Q values, multiplying by the gamma, basic Bellman equation here, and then we will be applying that acted queue to the queue values, a copy of the queue values, adding that to a Python list, pending that, and we have to concatenate it into a torch tensor to put it into the loss value, and we will be transferring that to the device again and calculating the loss. Then just basic propagation through that, and here we just load in the previously tested model. This is just for training here, and you can see we just create the Q learning agent. We generate the data set and we train it. And here for X amount of epochs, we will be generating a game's worth of replay memory and then training it for 40 batches. That's just something I was kind of playing around with. It could probably be optimized further if I had more time. And then you can see here is just an example images of the, you can see the current is a little bit before the next observation. And then, I don't know, here's the game being played.